All right, so the next topic we're going to be talking about is circular motion. Many real-world problems involve an object traveling in a circular path at a constant rate of speed. We can use our new friend Radian to help us out when we're trying to solve these circular motion problems. So let's take a look at what these might look like. So some vocabulary, notes, formulas, things like this around circular motion. Obviously, we use r to represent the radius, theta to represent the angle of rotation. In general, when we have it in the formulas, that needs to be in radians. Now, we might be given an angle of rotation in another unit, and we need to make a conversion in order to use that in our formulas here. S represents the arc length, which is the distance around the circular path, the linear distance that whatever is moving. V is the linear speed. So the linear speed is how fast around the circle that thing is moving in distance per time. And the angular speed is, again, how fast it's rotating around the circle. So how many angles per unit of time, how many radians per unit of time. Again, angular speed, just like angle, can be given in some different units other than radians, but we do need to be careful that when we use some of these formulas, we do make sure that our angle is actually given in radians. So we may need to convert that. In general, with these circular motion problems, we will find there is a fair amount of unit conversion. So I'm going to remind you of some things that you probably learned in some of your science classes for unit conversion. All right, so here's our first problem of circular motion. The wheels of a truck are spinning at a rate of 350 revolutions per minute. So we have our wheel here. Wheel is a circle. We can even make a little circle here. Sort of talk about this. Yeah, circle. So if we put that circle there, we can kind of look at, and I'll just delete that. So if we look at the radius of our circle, right, is the radius of the wheel. So that would be our R. And we know that for this problem, the radius of the wheels are 28 inches. That is our R. And they are rotating at a rate of 350 revolutions per minute. So they're making 350 full revolutions every minute. This is another way that we can represent the angular speed. So revolution is another way for us to do angles. So how many revolutions is another angle measurement. So angular speed, because we're doing revolutions, which is an angle per unit of time. Now, to solve this problem, or to solve things about this problem, we oftentimes will need to convert our angular speed from revolutions into radians. So that's what we're going to do here. We have a speed of 350 revolutions per minute. That would be 1 minute here. If we want to convert that, if our goal is to get into radians per minute, we will need to cancel out revolutions and put in radians, right? We will need our answer to be something in radians per minute. So we're going to be multiplying. So we know the relationship between revolutions and radians. We know that 1 revolution, I want in the bottom because I want to be able to cancel out that unit of revolutions, is equivalent to 2 pi radians. So by multiplying by this fraction right here, this one in the middle, I'm doing a conversion. I'm converting this unit of 350 revolutions per minute into radians per minute, because this fraction does not change this value. This fraction is equivalent to 1. 2 pi radians and 1 revolution are equivalent values. And when I write it as a fraction, that's the same thing as multiplying this by 1. It's just doing a simple unit conversion here. So when I do that, I'm getting, which is around 700 pi, well, exactly 700 pi. Though I am going to approximate that. I'm going to use 3.14 for pi, just to simplify the calculations here a little bit. So 700 times 3.14 is an estimated value of 2198 radians per minute. So that is our angular speed in the proper radians per minute unit that we need for solving some things about these circular motion problems. All right, so part B asks us to calculate the speed of the truck in miles per hour. So that's distance per time. We are trying to find the linear speed, V, of the truck. Fortunately for us, if we kind of go back to the previous page or have those formulas handy, we do know there is a relationship between linear speed and angular speed. So V equals R times omega, or W. So if you take the linear speed, it's going to be equal to the radius times the angular speed. Now, just doing this multiplication doesn't mean we're going to get the final answer here, because we want our answer in miles per hour. But we're dealing with radians per minute, and the length of our, or the length of our radius is measured in inches. So we're not going to get miles per hour right away. We're going to have to do a conversion for that. But let's go ahead and do the first step. So linear speed is going to equal 28 inches times 2198 radians per minute. So this is going to be in inches per minute when we do this calculation. Remember, radians is not really a unit. I'm writing it in here to keep it in mind, but it's not officially a unit. So when I do that, I'm getting a linear speed of 61,544 inches per minute. Now, that is not the appropriate units for this problem. That's not what we want our final answer in. So we're going to do a little conversion here. I like to save my conversions till the end for the most part, but sometimes you may want to do it kind of as you're going. It really just sort of depends on what you think is best for you or for the given problem. Now, inches per minute. We need to convert inches per minute into miles per hour. So I have 61,544, so 61,544 inches per 1 minute, right? That's what that's telling me. And my goal is to get this into some number of miles per 1 hour. So I want to convert here. Okay. I need to convert inches into miles and minutes into hours. So we could go in whatever order we really want here. I'm going to go first to the minutes into hours, right? So I know that there are 60 minutes. I know this needs to go on top so that I can cancel out the unit of minutes. I want to get rid of that. And I want to put hours on the bottom. So 60 minutes is equivalent to 1 hour. So if I multiply this fraction again, I'm multiplying by something that is 1. So I'm not actually changing the value, but I am converting it into hours from minutes, which is what I'm looking for. So there we go. I have 60 on top, and that's going to get multiplied there. Now, I'm going to keep going with my conversion. I also want to convert inches into miles. Okay. Well, I know that 1 mile is 5,280 feet, and there are 12 feet in a mile. So I'm actually going to do a little quick calculation here. So 12 inches per 5,280 feet. So multiplying those, I know that in 1 mile, there's actually 63,360 inches. And again, inches are going to go in the denominator here because I will want to cancel that unit out. And miles need to be in the numerator because I want that to be in my numerator for my final answer. Now it becomes a simple matter of doing this calculation. Multiply things that are in the numerator together, divide by what's in the denominator. So I'm going to do 61,544 times 60. And then I will divide that by 63,360 to come up with an approximate speed. I'm going to go ahead and round this to 2 decimal places of 58.28 miles per hour. So that would be our linear speed in the appropriate units. So you can see how these problems involve quite a bit. We got to make sure we understand the angle and rotation aspect of these problems, but also this unit conversion, which can really bog these problems down. You want to be real careful as you're doing it. I really like drawing them out in this way, just like you would have done in maybe your first physics class or perhaps chemistry. I'm going to go ahead and clear this and keep moving forward. All right, number 2. The radius of the Earth is 3,960 miles. That's an approximation. If a person is standing on the equator of the Earth and the Earth is spinning on its axis of rotation at a speed of 1 revolution per day, That's what it does, right? How fast? What's the linear speed of the person? So, even though the Earth is a sphere, we can think about it in terms of a flat circle in this problem. I'm not saying that the Earth is flat. I'm saying we're talking about a person which is standing on the equator, and this circle is representing just my equator. So we have a person on it. They're standing there, and they are rotating around the Earth pretty fast, right? Because the Earth is huge, and it has to make a full rotation in a day. So it's actually moving pretty fast here. And we said that our radius was, what was that number? 3,960 miles. So oops. I'm just going to make a quick note of this. 3,960 miles. All right. How fast is the person moving in miles per hour? All right, so that's linear speed, that is v. So there's a couple ways we can calculate v. We can calculate it in terms of knowing the radius and angular speed, which is a possibility here. We can also calculate it in terms of knowing the arc length, the distance that a person is traveling in this case per a unit of time. We could go about this in both ways because we do know the angular speed in rotations, and we do know the radius of the Earth. We also could sort of figure this out in terms of this problem. It really just kind of matters on your preference here. I'm going to go ahead and use this one, but we could get this in several different ways. So I'm going to go ahead and get rid of that other formula. So I know my radius, so that part is great. But my angular speed, which is currently 1 revolution per day, needs to be converted to radians per hour, I think, because we're dealing with miles per hour. So let's go ahead and convert this to radians per hour. So we first know that we need to get this in radians. So 2 pi radians per 1 revolution. So we can cancel that out and kind of get it there. So we're going, so now we have a answer of 2 pi radians per day. But again, we want this per hour. So 1 day is equivalent to 24 hours. So if we kind of convert here, we end up with 2 pi over 24. I'm going to go ahead and multiply that out, or divide that rather in this case. So 2 times 3.14 divided by 24. Okay. Maybe I don't want to do that. Maybe I just want to do this here. So this is equivalent to pi over 12 radians per hour. So that is our angular speed in radians per hour. And I'm leaving it this way since we are dealing with really big numbers. If I go ahead and round too early, this could be a problem. So now I can kind of simply use my formula here of linear speed is equal to radius times angular speed. So my linear speed is going to equal my radius, which is 3,960 miles, times pi over 12. And that's going to be in radians, which remember is not really a unit, so I can get rid of that, per hour. So I'm getting my final answer in miles per hour, and I'm going to multiply this all out to get an estimate. So I'm doing 3,960 times. I'm going to make a fraction for I'll use pi again because we're dealing with large numbers. Pi over 12. And my calculations are this. So that's around 1,036.7. Let's just go ahead and round that to a whole number. We'll just say that we're at 1,036 miles per hour. That is very fast. I don't know about you, but I've never gone in anything anywhere near that fast. So I suppose an airplane is perhaps not near there, but is pretty fast. So it's faster than anyone's really traveling. But That's how fast a person is moving around the Earth, if we think about the rotation of the Earth spinning at the equator in this case. All right, so what is the distance that a person travels in 10 seconds? Okay, 10 seconds. That's a short amount of time, but we're moving really fast. So we want to know the distance they travel. So we want to talk about from here to here. Like, what is this distance? What is the arc length in 10 seconds? Well, there's a few things that we can do here. So we do know that there are a few formulas for arc length. So we know that the arc length equals the radius times the angle. We know that the linear speed equals the arc length over time. So we can do sort of all sorts of things here. Just kind of depends on what we know or what we could figure out. And there's almost always multiple ways to do these problems. In this case, I don't know the angle that's created in 10 seconds necessarily, right, to find that. So this one doesn't actually seem that useful. I could figure that out, but I don't know that yet. Whereas on this one, I actually know a lot of this already, right? I know the velocity, the linear speed. We already calculated that. We know the time that we're dealing with. We're dealing with 10 seconds. So actually it seems like this might be the way to go. So, and that S would be our answer, our arc length. So I'm just going to kind of quickly solve this formula in a little bit different way, right? If I multiply by t on both sides, I have that my arc length is equal to velocity times time, my linear speed times time. So in this case, I can kind of make this problem work a little bit better. The only problem that I have here is my speed, my linear speed, and my time, the units aren't really matching up here, right? If I'm doing miles per hour and I have seconds, there's an incompatibility there, so I'll need to do a little bit. So let's put them both in miles per, or in hours. So 10 seconds is there is 60. Oh, sorry. There are 60 seconds in a minute. So 10 over 60. And there are 60 minutes in an hour. So I'm running out of space here. I'm sorry. This is just going to be a little scratch work off the side. These problems do require a lot of space. So let me give this part its proper space, and then we'll just kind of keep the final answer to work with. So 10 seconds is 1 minute is equivalent to 60 seconds. So that converts it into seconds, or sorry, to minutes. And then 1 hour is equal to 60 minutes. So really what I'm doing here is I'm dividing by 60 twice. So if I do 10 divided by 60 divided by 60, that's the same thing as 1 over 360. So I'm going to do it that way. So 1 over 360. Right, I could sort of cancel some things out. Cancel out the 10, so I get 1 hour. And then 6 times 60 is 360. So I get 1 over 360 of an hour. Apologize for the lack of space. All right, so now we can kind of go about doing this problem. I had to kind of synthesize the units, make sure they were in the same units, miles per hour and hours to make this work. So next, let's actually solve the problem. So S, my arc length, is equal to my speed, which we just calculated, of 1,036 miles per hour. And we are only going to be traveling for 1/360th of an hour. Cancel out hours, and we're simply dividing by 360 here. So 1036 divided by 360. So that's around 2.87 repeating. So 2.88 miles. We round this at some point. Again, we're not really specifically asked to come up with a specific rounding or specific accuracy. So I'm just rounding this because I got 2.877777, right? Rounding that. So in 10 seconds, so just counting to 10, you know, you're going to travel that far because we are spinning around very fast. All right. Last one here for some circular motion problems. The Singapore Flyer is the second tallest Ferris wheel in the world. It reaches a 550 feet at its peak and performs one rotation every 2.5 minutes. Okay. Reaches its peak. So its peak is its overall height. So that would be from the top all the way down to the bottom. So the radius in this case is going to be half of that, or approximately half of that. So for this problem, I'm going to assume my radius is half of that, which would be 275 feet for my radius. Just assuming that. Again, there's probably some discrepancy where you know, the Ferris wheel isn't all the way on the ground, but let's just assume that it roughly is. All right, and performs one rotation every 2.5 minutes. Okay, so that is kind of an angular speed, right? Rotation is an angle per time, so that is an angular speed. So that's one rotation per 2.5 minutes. If we want to go into radians per minute, we will need to multiply this to cancel some things out. So one rotation is equivalent to 2 pi radians, right? So that cancels out our unit of rotations, and we're going to be in radians per minute now. So that's 2 pi over 2.5 radians per minute. It's a weird unit, and let's just go ahead and estimate that. So 2 times 2.14 divided by 2.5. All right, so I'm getting this to be 2.512 radians per minute. That is our answer here. Exact or decimal estimation, you know, however we want to do it. Now, calculate the distance a rider would travel in 1 minute. Okay, so distance. So we are looking for an arc length. We're looking for like a person is up here riding it, and they're going for 1 minute, and they end up here, and how far is that? There's a few ways that we could do this. We could figure out how much, what fraction of a rotation that was. Again, we're looking for S. We're looking for an arc length here. So let's just think about the different formulas that we have. So S equals R theta. V equals S over T. Yeah, I mean, we need to do sort of one of these things to kind of get to this. I'm inclined to use this one this time, and I'm not sure exactly why. Hopefully, I can maybe convey it as we're doing it. So we know the radius, so that's good. And the angle shouldn't be too hard to figure out. We do need to be careful that our angle is in radians when we're using this formula. We need to figure out, again, let me draw it on the picture here. We want to figure out if this is how far we're going to go, and this, we need to figure out what that angle is, or what fraction of a rotation we are dealing with. Maybe that blue is not the best. We'll do it in green. In a minute. And we're going to make use of this fact up here about the one rotation every 2.5 minutes. So I know that 1 minute in comparison to 2.5 minutes, it's not 2.2 minutes, is, and I can do an equivalent fraction here. If I multiply this by 2 units, that's that means that we're going to be going 2/5 of the way around the circle. So this is equivalent to, we're going to do 2/5 of a rotation. That's what this fraction is equivalent to. We could even get a decimal there. So 2/5 of a rotation, or 0.4 of a rotation. So I can use that to figure out my angle. If I know I'm going 4/10 or 2/5 of a rotation, I can multiply that by 2 pi. So I can do, oops, I can do 2/5 times 2 pi. So that's going to give me my angle here. That's going to be 4 pi over 5 radians. So that is the angle that we need. And I'm going to do a little bit of erasing here. So hopefully that kind of made sense in terms of what I was doing. We know that a full rotation is 2.5 minutes. So if I'm only going for 1 minute, I'm going 1 minute out of the full 2.5 minutes that it takes for rotation. So I figured out sort of what fraction or what decimal of a full rotation it was, and then multiply that by 2 pi to convert that into radians. Hopefully that kind of made sense in terms of what I was doing there, at least after the explanation. So now it just becomes a matter of using my formula to calculate. So the distance that I'm going to travel, the arc length that I'm going to travel, or a person will travel, equals the radius of 275 feet times 4 pi over 4 or 5. And again, we'll just do a quick estimation of 3.14. So I'm doing 275 times 4 times 3.14 divided by 5. So we get this to be approximate distance that this person is traveling in a minute is around 690.8 feet. So that is the arc length that is being traveled here after a full minute of a rotation. I guess I kind of underestimated this angle, but you kind of get the idea, I hope. Okay, and let's kind of wrap things up. We're not going to be doing the area of a sector. This is something we decided to drop out, but so that's it. And we'll spend some more time in class kind of going over some more circular motion problems, and hopefully I'll be able to answer your questions. But yeah, see you guys next week.